Thanks, Corsin. Thank you, Corsin. And thank you all for coming. It's such a pleasure to do this seminar. I had heard a lot about it in the past. And I apologize to my European friends that this is kind of late in the afternoon, but it's still only 8 o'clock in the morning. So hopefully I am wide awake. You may not be, but let's see. So I'm going to walk you through first the basic science of disordered rock salt cathodes, and then I'll end with some of the new work that's maybe more technology specific, but some of the exciting work, some of it which is not quite published. But maybe a bit of introduction first. That you've seen slides like this. Demand for lithium ion, which is clearly the winning technology in energy storage, is ramping up dramatically. And while there may be temporary bumps in the road, we have seen a decline in or at least a decline in the growth of the lithium ion market because of the decline in the EV market. There clearly is going to be a demand that's in the order of multiple terawatt hour of lithium ion. And to put that in perspective, today we produce of the order of maybe about 1 terawatt hour of lithium ion. The cathode class has become pretty much sorted out, right? We either have think of it as the high energy class of materials, the NMC series, which sort of successfully made a transition from containing a lot of cobalt to containing very low amounts of cobalt, now in NMC 811 and even 955. So the transition from cobalt to nickel is virtually complete. And then on the lower end of the market, the lower energy density, we of course have lithium iron phosphate, a material that when it was invented by Paddy and Goodenough, now almost 30 years ago, we weren't really sure it was going to make it. But today's cathode market is almost 50-50 split between NMC and LFP. And that comes because of the dominant position of LFP in China. If you actually were to look at the US and European market separately, that is still much more heavily on the high energy density side of NMC. So NMC is an amazing cathode material that we could in principle keep on using. There are some issues to concern. One is the issue with nickel production. And to put in perspective, order of magnitude for a terawatt hour. So let's say you want to make 3 terawatt hour of NMC worth of lithium ion in 2030. You need somewhere between 2.5 and 3 million tons of nickel. As little back as 2020, we only produced worldwide about 2.5 million tons. So basically, you would be taking all of that. Recently, the production of nickel has ramped up considerably, mostly due to the opening of new mines and new refinement facilities in Indonesia. But there are certain issues with nickel, right? We are operating at the edge of what the market can tolerate in terms of the nickel demand. So there are potential supply limits. The price of nickel, even though it's down quite a bit, will always limit how low you can go with high nickel NMC batteries, because the price of nickel truly shows up in the cost of a cell. And maybe some of the worrying thing is that this increase that you see here, which is to a large extent due to Chinese refinement in Indonesia, has significantly increased the CO2 and sulfur oxide emissions that are associated with nickel. And that's because what's actually really happening is that lower grade nickel ore bodies are being accessed, so-called class 2 nickel and lower concentration ore bodies are being accessed, and that leads to higher CO2 emissions. This is something that will certainly come up, certainly as political landscape is changing for EVs, that the CO2 emission associated with lithium battery production, both on the lithium side and on the nickel side, has actually been increasing dramatically, to the point where, depending on your electricity mix, the payback now in CO2 for driving an EV can be anything from below a year to 5 years. And in a state in the United States like Wyoming, where there is no clean electricity, it's actually infinite, the payback. And then the other issue is deforestation. So a lot of the new nickel mines in Indonesia are in rainforest territory. So, and if you want to read more about this, an article that I really should credit Elsa Olivetti from MIT mostly to, which talks about sort of the environmental issues with nickel. There are safety issues, of course. Hot and this is no pun, hot off the press. This happened just a few days ago. California is home to some of the largest energy storage on the grid in the world. One of the largest is what's called the Moss Landing plant, which has two parts and had now one of the largest fires, I think, in the history of batteries. Almost 1 gigawatt was destroyed. This was built for Pacific Gas and Electric, which is our large electrical company, but is built by Vistra Energy, a Texas company, but uses LG and MC. There is a Tesla part to the plant, which was not destroyed, but this is basically going to put a serious crimp in getting lithium ion on the grid. This was a serious fire. A whole town was evacuated. There was major worry about HF pollution in the air and things like that. So, and this happened just a few days ago. So the real question, if you do cathode design, is really, can we get the best of both worlds, right? Can we get the energy density of NMC-like materials with the price and safety of LFP and with earth-abundant metal, so we don't have to worry about supply and toxicity issues? So I think I've been doing cathode design for maybe more than 25 years, and I think there's a few lessons we've learned from way back in the 90s that while we were always heavily focused on the materials quantities, the specific energy, the energy density of the material, we have learned that other things matter too, and lithium iron phosphate is a good story to that effect. If you actually look at the material, so the cathode, and you look at the energy by weight or volume and you compare it to an MC, you lost basically almost 25% on weight, so specific energy, and almost 50% on energy density. But by the time you go to the pack, those you still lose, but you lose considerably less. And so that's really the main reason why LFP has become competitive, because what's lost at materials and at the cell level is partially gained at the pack. And this is mostly because of the inventions done by BYD in so-called blade technology, where because the charge state of lithium iron phosphate has high thermal stability, you can actually make very large cells, and so the volumetric efficiency of the pack is much higher. The volumetric efficiency of an LFP pack, so in the sense of if you take the volume taken up by cells versus the empty volume, is almost double that of NMC, and that's mostly due because of the high thermal stability of LFP. So I think what we've learned from this is that yes, you should look at materials properties, but you also should think at other properties that affect the ultimate energy density that you will get in a pack. So that brings me to my design exercise, and the space of metals that you can use with is sadly quite small. So if you're going to make terawatt hours worth of material, you're going to need millions of tons of it. And if you look at the world production of 3D transition metals, so let's say you need something in the 5 to 10 million ton range so that you don't take all of it, right? Because the world wants these metals for other things. There's really only 5 metals, titanium, chromium, manganese, iron, and copper. I've listed here roughly the price of the precursors, either the metal or the oxide precursors. And of course, copper has been challenging to work as a redox couple, right? Because of the different valence state, all prefer extremely different coordination. So it's very different to do intercalation chemistry with copper. And then titanium is kind of low voltage, right? That's why we use it on the anode side. So we basically have chromium, manganese, and iron. Iron is great in polyanion systems where the voltage is reasonable. If you use the iron 2 to 3 redox couple in close packed oxide, the voltage is too low, so you'd have to use 3 to 4, which tend to lead to a high amount of oxygen redox. So that leaves you basically with chromium and manganese. Chromium is a wonderful element. It's cheap. It has multiple redox states. You can make fabulous cathode materials actually with chromium, but there's certainly an societal and industry aversion to chromium because of the toxicity of chromium-6. If that could be overcome or managed, I should say, chromium is really a leading element for making probably the highest energy density cathodes you can imagine. But for now, I'll focus heavily on, towards the end of the talk, on manganese, which of course is inexpensive, thermally quite stable in the 4+ state and easy to handle. So if you're going to design new cathodes, I want to go back to, why can you not put all these elements in layered materials? Why can't you do layered chromium oxide and layered lithium manganese oxide? And that's been known for now over 20 years, but it's used to remind ourselves that there's a reason it's called the NMC class, and the only redox active materials in the NMC class are nickel and cobalt, and that has to do with their mobility in close-packed oxides. So if you take a layered material, and I have sort of a cartoon here, and you kind of pull lithium out, what actually happens if you go over about half lithium extraction is that metals start to migrate into the lithium space. And because of their higher valence state, they actually contract the oxygen layers around them. And because of that contraction, the lithium mobility goes down. And that's shown here in an old calculation we did. This is actually the activation energy for lithium motion as you contract the slab space. And this is a dramatic effect, right? Even like 1/10 or 2/10 of an angstrom raises the activation barrier by several hundred millielectron volt, which would basically mean the difference between lithium mobility and nothing at all. And the reason is actually fundamental related to the crystal structure of these materials. These materials are close-packed oxides, meaning that the oxygens are essentially stacked FCC with some distortion. And in any close-packed oxide, to move from an octahedral to another octahedral site, you have to migrate to a tetrahedral site. So the octahedral site's phase share with this tetrahedral site. And when lithium migrates through there, it is in close contact with the transition metal. And this electrostatic interaction, this close electrostatic repulsion, is what sets the activation energy for lithium hopping. And now you see why the slab spacing matters. The slab spacing actually sets the size of this tetrahedron. So if the slab spacing is very large, then the lithium can stay far away from the transition metal. If the slab spacing gets contracted, then lithium will not want to hop through that tetrahedral site. And that's why if you look at the lithium diffusivity in layered materials, it essentially follows the slab spacing. When the slab spacing is high, the lithium mobility is very high. At the end of charge, when the slab spacing contracts, the lithium diffusivity collapses as well. So the fundamental problem is the migration of these things. And there are only two metals that are essentially don't migrate across multiple valence states, and that's nickel and cobalt. Manganese 4+ also doesn't migrate, but when you reduce it, it migrates. So 3+ and 2+ migrate. And that's really why we will only have layered materials with nickel and cobalt. So NMC, basically what you see is what you get. We're not going to do fundamentally different redox chemistry in layered materials. So about 10 years ago, we tried to rethink this problem and said, well, we had all tried forever to make layered materials. So we were thinking, how about if we don't need the layered crystal structure, we could in principle use any transition metal. And that meant rethinking the diffusion, and that's what ultimately led to the disordered rock salts. So the whole idea was that if you remember, the real problem is this lithium transition metal repulsion in the activated state. If you were not to have a transition metal there, but like a vacancy or maybe another lithium, then the electrostatic interaction would be much less, because you would have 1+, 1+, or 1+ against 0, whereas the transition metal is typically 3 or 4+. So that's how we got to disordered rock salts, that if you disorder the cations in the rock salt crystal structure, you statistically create all kinds of environments around this tetrahedral site. And the one that's really intriguing is this one. It's the one where there's only lithium, or as it's now referred to, it's a zero transition metal environment. Because what you see here is that if you actually start to extract lithium and make some vacancies, then this lithium, when it's in the tetrahedral site, in the activated state, will have very little electrostatic repulsion, which means it will not suffer a lot from this lab space contraction. And that's what you see in calculations. If you actually, this is a little hard to see, but if you look at what's called the 1TM channel, which is this one, which is active in layered materials, that one actually, the activation energy goes up a lot as you contract the tetrahedron. Whereas if you take a 0TM channel with only lithiums around it, you actually have still fairly low activation energy even when you contract that tetrahedron. And so the idea was that these channels are active for diffusion even in disordered materials. But of course, you need enough of them and they need to percolate. And what we found was that if you could make them percolate, but you needed 10% lithium excess. If you had 10% lithium excess, then, and the ions were all randomly distributed, and I'll come back to this, you could make them percolate and you could actually get lithium transport through a fully cation disordered material. And the concept works. It's shown by several people, including ourselves, in different materials. This is kind of between 5 and 10 years old. This work, there's our work in science on the molychromium system. Here's a stem data of a fully disordered material. And what you see is that this thing really cycles almost a full lithium per formula unit. Here's a manganese niobium one that we did and some people in Japan. And then there was the early work in Europe by Chen and Fichtner on vanadium oxyfluorides, which were disordered and also cycled, though with low rate capability. And at least the proof of concept worked to the point where, because we don't need a specific cation ordering, we can work with almost any metal in the periodic table. And I've sort of listed here almost all the cations or anions that have been used in disordered rock salts. And you can see almost every single transition metal has been used. There are other things because of the partially disordered nature. You can substitute some of the oxygen by fluorine, which I'll talk less about today, but which tends to give you a very good surface stability. Because what happens is even if you lose 1 or 2 layers of oxygen, you get an enhancement of fluorine at the surface. That often even happens in the synthesis, and so you have essentially a fluorinated cathode surface, which has extremely high stability against oxidation. There's so much data that we recently published a paper where we showed you can do machine learning on these data, and you can actually predict voltage profiles as a function of cycling for many of the different DRX chemistries. You can make very high capacity DRX materials. For example, here's a highly fluorinated. This is a manganese 2+ to 4+ redox couple. You can go over 900 watt-hours per kilogram. Here's a partially disordered spinel, which is over 1100 watt-hours per kilogram with extremely high rate capability. These materials are sort of exciting proof of concepts. They're certainly, in some cases, challenging to work with. And I'll come back to that because towards the end, I'll go towards the more practical DRX materials. You can make high rate DRX. A lot of DRXs have still fairly poor diffusivity, but that doesn't mean that all of them do. If you do high entropy ones, you see discharges up to 0.5 amp, 2 amps per gram. If you do slightly more partially disordered materials, this is a chromium manganese. Here's kind of a discharge at 100 milliamps per gram. There are other sort of interesting, things you can do if you go to early transition metals in DRXs. Things like molybdenum, vanadium, you can actually make extremely low strain and even zero strain DRX materials. The original DRX that we published, the molychromium one, this is actually the volume of the unit cell as a function of lithium content. As you see, there's virtually no volume change. And both Professor Yabuchi and ourselves in Japan have shown several vanadium-based DRXs, which essentially have no volume strain at all over a very large capacity range. The volume changes of these materials are sort of 1% or less, and in some cases are even negative. And also because they are cubic, the volume strain is isotropic, unlike in layered materials. So I want to come back a little more to the structure because that become important is that, so if you look at these materials in X-ray diffraction, they just look very simple. They're like they're truly a rock salt, so fully cation disordered. But what we have learned over the year that there is subtle structural complexity that you cannot see in XRD, but that you have to control by compositional issues or by processing. And most of them relate to what's called cation short-range order. So cation short-range order is actually the statistical preference for ions to surround themselves with themselves or another ion, a preference that's different from random. Okay. And if you remember, our percolation theory was built on fully random cations. And if you remember, what we want is these zero TM channels. But actually, in most cathode materials, because of electrostatics, there is a preference when you have a lot of lithium to bring a transition metal nearby, because that gives you a local charge balance. And what you see is if we get this one TM channel instead of this zero TM channel, we will be destroying a diffusion path. And the way you see short-range order is extremely hard to detect in XRD, but you clearly see it in electron diffraction in TEM, and it's typically seen as this kind of diffuse scattering between the Bragg peaks. You can also see it in single crystal XRD, but of course that's a lot harder to do. So I'm going to show you a dramatic effect of short-range order. Here's two DRX materials that are almost exactly the same. So the active redox species here is manganese. Zirconium and titanium are just 4+ stabilizers, as we call them. They're actually elements with no d electrons. So fully stripped d electrons tend to enhance disorder. But if you look at these materials were prepared in exactly the same way. They have very different short-range order. You see that from the different diffuse scattering in the electron diffraction. And if you look at their performance, it's also very different. The zirconium one has very poor performance. This is the amount of lithium you can cycle, whereas the titanium one has much better performance. Again, so these materials have the same particle size, same processing, but the short-range order is very different. And you can model that, and actually this is the percolation shown in the zirconium one, and this is in the titanium one. And as you see in the titanium one, the short-range order is much more favorable to make zero TM channels. So you have a lot more of them, so you have much better diffusion paths, whereas in the zirconium, you have these barely percolating diffusion paths, so which is consistent with the poor performance. So what can you do to control the short-range order? And I want to stress this is something you don't see in XRD, right? You can have materials with the same XRD with different performance. So we've come up with a few ways to control short-range order. I'm only going to discuss two. One is sort of a cute one, maybe less practical, but it's been known in the field of metals that you can use high entropy concept to decrease short-range order. So we kind of read about that actually from one of my colleagues here in Berkeley. And then I said, oh, let's try this in DRX cathodes. So we did a systematic experiment where we mixed more and more metals in the DRX. And so I'm going to show you something with 2 transition metals, 4, and then 6. And then we also even did 12 just for the sport. So if you work with 2 transition metals or 4 transition metals or 6, so what you see is this is 2, you get significant short-range order. This is 4, and this is 6. By the time you have mixed 6 transition metals, your short-range order is almost completely gone. And what you see is if you look at the performance, the more transition metals you have, even though we have the same redox capacity, we get higher specific energy. And this is same particle size, same electrode formulation, discharge at the same rate. So clearly sort of evidence that controlling the short-range order improves the rate capability and thereby improves the amount of capacity you can get at a certain rate. And actually, by the time you're at 6 metals, you can actually do respectable discharge rates, right? So these are experiments where we charge and discharge at different rate. And, even at 500 milliamperes per gram, we get quite respectable discharge capacity in these materials. But by far, the most practical way to actually control the short-range order is to control the heating and cooling profile. So what we have learned in DRX is to actually control the annealing time. You really want to minimize the time spent at high temperature, because what I'm showing here, this is in situ electron microscopy that was done by my colleagues at NSEM. After 5 minutes above 900 Celsius for this specific composition, the rock salt has formed, but there's no short-range order. And then as you let the material sit, it actually tends to form short-range order. So the lesson is here that in the synthesis, the rock salt forms very early, but the short-range order forms only with time. And you see that in the performance. If you look at the performance Long means long annealed, short means short annealed at different rates. At low rate, you barely see any difference, but at high rate, you actually see quite a difference. And so again, because in the short anneal, you have minimal short range order, so you have better transport characteristics. So in the second part, so this is sort of the basic landscape of DRX. And again, you have to remember that when somebody talks about DRX, the first question should be like, what specific material? Because, just like NMC, DRX is a whole class of materials with many different transition metals. It's in some sense broader than the NMC class. You can have different redox couples. You can have different stabilizer. You can different amounts of lithium excess. You can have high fluorination, low fluorination, or no fluorination. So today I'm going to talk about a more limited class, and this is the one that the Department of Energy and us picked together. A number of years ago, a DRX consortium was set up between multiple national labs, and the first version of that consortium was to start looking at the fundamental challenges in DRX materials, where they are solvable. And that led us to what is now, I would say, close to the end game, which is single crystal DRX, which I'll talk about at the end, which has extremely stable cycling capacity. So chemically, the class of materials that we focus on is the lithium excess manganese titanium system, mostly oxide, but often with light fluorination. And the reason is relatively obvious. This is potentially extremely inexpensive. Manganese precursors and titanium precursors are very cheap. You can use titanium oxide. You can use various forms of manganese oxides. You can even use manganese carbonate if you want to. And the lithium source that we typically use is lithium carbonate, though, of course, you could use the hydroxide, even the lithium oxide if you really wanted to. These materials are made by basic synthesis. I know there's a lot of confusion. Some of these exotic materials that I showed you in the beginning are made by heavy ball milling. These are actually just made by standard solid state synthesis, although the consortium is also looking at novel ways like combustion synthesis. And towards the end, I'll show you some single crystals made by molten salt synthesis. They have certain advantages. You can make these materials in 5 minutes at high temperature. So they can, in principle, have particularly high throughput on the synthesis. So if your precursors are well mixed, these materials only need to spend about 3 to 5 minutes at elevated temperature to make the DRX. They have excellent stability, and that's in part because the top of charge is only manganese 4, which is a stable redox state, as I showed you before. Manganese 4 is stable in air. And they have virtually no oxygen redox activity, unlike, say, the early DRXs. A good number to keep in mind is the crystal density is about 4 grams per cc. So that's lower than NMC and higher than lithium iron phosphate. And again, whereas a lot of the research work has very high amount of carbon in the electrodes, and that's because particles used to be heavily milled. Today, there's some really fascinating work done by Donghwa Seo at KAIST in Korea, together with Jin-Yuk Lee, who's one of the co-inventors of DRX, who's at McGill, showing very low amounts of electrodes with very low amounts of carbon. So I'm going to show you two materials. The slightly older material, which is a typical solid-state synthesized material, so typically just mix and fire and then mill it, because solid-state synthesis often leads to irregular particle size distribution. And then I'll show you the most recent work on single crystal, what's called delta DRX. So one thing about the high manganese content materials is that they have sort of unusual electrochemical behavior. So if you take a rock salt, this is a low lithium excess rock salt, high manganese content, right? So this is manganese 3 plus all, so you can do all the redox capacity on manganese. And about 10% titanium stabilizer, this is no fluorine. When you cycle these materials, independent of the voltage window over which you cycle, they actually increase their specific energy with cycling. And it starts from a relatively low number, so in the 400 to 500 watt-hours per kg range, going all the way up to 800 watt-hours per kg. I'm showing that here over longer term, you get this rise in capacity, and then you get this sort of slow decay. The slow decay is actually not materials decay, it's actually electrode issues. This is clearly established because of the small particle size in these milled materials, you get a loss of contact with the carbon, and you get EC breakdown, so the electrolyte breakdown, which builds up polarization. But I'll come to that issue. So it's interesting, if you look at the voltage profile and the rate capability, there's clearly some change going on. What happens actually that as this change proceeds in the material with cycling, the rate capability goes up. So this is the discharge rate capability in the first cycle, which is quite poor, right? By the time you're at 200 milliamperes per gram, you've lost half your capacity. But in the 20th cycle, that starts to look much better. Now you can relatively easily get 200 milliamperes per gram in these materials. But what you also see is that the voltage profile has transformed, has been modified from this sort of typical slopy profile of a disordered rock salt to something that has plateau-like behavior. And turns out these aren't really plateaus. They never truly become flat, and I'll show you that later. They really are sort of more plateau-like. And if you look at the diffraction as a function of cycling, you see the typical rock salt peaks, but then with cycling, you see these things appearing that are certainly reminiscent of spinel. And so more general, I would say they're reminiscent of cell doubling. So the rock salt unit cell doubles just like in a spinel. So the question is, have we actually made spinel by cycling? And I'm going to show you that not really. So spinel, of course, is a very known lithium manganese oxide. Spinel is a very well-known cathode material. Here's the typical voltage profile. Commercially, only the 4-volt region has been used. And there was a 3-volt plateau that we could never use commercially because that's a two-phase reaction. That's why this is so flat. And a two-phase reaction, by definition, occurs inhomogeneously. So you get one part of the material that completely fills while the other one doesn't. And that causes enormous strain. And that's in part why the material degrades extensively. In contrast, if you look at this transform material through cycling, which we refer to as delta, if you do in situ diffraction, you see something very different. So again, this is a regular spinel. And when you cycle a regular spinel through the 3-volt plateau, you clearly see this peak splitting, right? Which is reminiscent of the two-phase reaction. You have a new peak appear and the old one disappear. On the other hand, if you look at what's called delta DRX, you have a continuous change in peak position. So even though it looks like a plateau, this is clearly lithiating and delithiating as a solid solution. So the question is, what is the structure of this material that makes the material so good, and could you induce it without cycling, right? Because nobody wants a battery that you have to kind of like try out for 20, 30, 40 cycles to make it actually work to your advantage. So the structure of delta DRX was a bit of a puzzle. We had certainly historically known from theory that when you reduce manganese from 3 plus in the 3 and the 2 plus state, manganese is quite mobile in rock salt environments, and that's also why you can never make a layered lithium manganese oxide cycle, because the manganese just moves all over the place. And obviously the ground state that it wants to evolve to is usually spinel. And so it's no surprise that what it actually forms is related to spinel. If you actually look at electron diffraction, you certainly see new reflections that are reminiscent of spinel. And if you do 4D STEM and you use appropriate Bragg filtering, you see this microstructure. And this microstructure is sort of on the scale of like somewhere with 5 to 10 nanometer, and you actually see the lattice fringes. And what these actually are is they are different variants of spinel that have formed from the rock salt. And the boundaries that you see here so beautifully are actually antiphase boundaries between the spinels. So what may be surprising to you, and was certainly a surprise to me, is that you can, if you nucleate spinel from a rock salt, there are 8 distinct variants. I always thought there were 2, but there are actually 8. There's, of course, the variant that comes from translational change, changing the 16C and the 16D site. But for each translational variant, there are 4 orientational variants. So if you take a disordered rock salt and you randomly start to grow a spinel in certain place, and you do that in another place and another place, you will have 8 different variants growing. And what you're seeing here is the impingements of these variants on each other. And this microstructure is remarkably stable. If you look at this at longer times, it still looks exactly the same. So it does not coarsen, which still puzzles us. This maybe because there's very little energetic driving force to coarsen, because the whole material is transformed to these spinel domains. If you actually look at enlargement of the stem, you actually see antiphase boundaries. So here you're actually seeing 2 domains that are orientationally the same, but they have a shift in 16D, 16C occupation. You actually see beautifully here how the lattice fringes shift. You have an antiphase boundary. So what is delta DRX? It's essentially nanoscale domains of different orientational and translational variants of partially disordered spinel, and it's separated by antiphase boundaries. The coherence length of these domains is very small, and that's why you don't have a first order phase transition. So we've known for a long time that if you can keep material size small, like nano-sized, then you don't have first order phase transition, so you don't have a two-phase region. But what's maybe unique here is that these are not nanoparticles. These are nanospinel domains in a large rock salt particle. And that's why if you look at the rocks, at the diffraction peaks, you see very sharp peaks, which are the rock salt lattice peaks. Remember, the rock salt lattice is common to spinel and to the disordered rock salt. And then you these superstructure reflections, which are broad because they are the spinel ordering in the rock salt lattice. So this material performs extremely well. I'll show you some more electrochemical data in a second. But a challenge for us to make this practical was how could you induce this material? You know, our original work and that from Guiying Chen at LBNL showed that you could certainly get this with cycling, but again, it's not very practical. So we've come up with a few different ways, and I'm showing here 2 more that are just been published. One is you can actually delithiate the material and slightly heat it, and it will transform to delta. That may or may not be practical because you have to take lithium out of the material and then re-lithiate it before you put in a cathode. But the one that may be the most practical is to do a specific pulsing regime in the formation cycle. And that we just published. If you want to read, it just came out in Advanced Materials. I actually think this is 2024. Sorry about that. And that is what led to the use of single crystal DRX. So the way that's done is that basically you take the material and rather than cycling it, you give it a specific set of pulses. This isn't really the most optimized pulsing sequence that I'm showing. We do that at slightly elevated temperature, which is also typical for formation cycles. We do it at 50 C, but you could do it at 40 C, you could do it at 60 C. You pulse in a particular regime, and that pulsing regime is now close to optimized. And that actually causes the transformation. So by the time then you actually put the cell in use, you already have delta DRX available. So that's let the improvement that delta DRX gives you in rate capability has allowed the use of larger single crystal DRX. So again, in the past, a lot of this early work I showed you in the talk were materials that were heavily milled. So the single crystallite size would be like 1 to 200 nanometer. And that's because of the often somewhat poor rate capability. So now when we can increase the rate capability, you can actually use larger single crystals. So here's sort of 2 to 3 micron single crystals. They're very homogeneous. These were made by molten salt synthesis, but just like people are trying to make single crystal NMC with direct salt state synthesis, we're kind of trying to do the same. So these materials work extremely well. So this is after the formation cycles that have been where pulsing has been done. So here you see a discharge curve. This is the first cycle. There's still a bit of remnant transformation. So by the 50th cycle, the capacity is larger, but there's actually 2 lines here, which is the 50th and the 100th cycle. So these materials are exactly on top of each other. So there's virtually no degradation at all in this material. And you see that in the specific energy. If you start cycling the material after formation, the specific energy creeps up a little bit because of the remnants of the formation. And then here it taps out and is flat at about 625 watt-hours per kilogram. Again, which puts you at the low end of the NMCs, well above lithium iron phosphate. Even at 50 Celsius, these materials have good retention. There is a little bit of capacity fade at 50 C. This is still not all materials fade. Some of this is actually, we have major issues with EC breakdown, electrolyte breakdown at 4.8 volt. And to newer charging protocols of Delta actually only go to 4.6 or 4.7. Unlike other lithium excess materials, there is no voltage fade at all. Again, in the remnants of the formation, the voltage creeps up and then is extremely stable. Average voltage about 3.3 volt. Some unpublished work that you can, if you play with the single crystal particle size, you can get the specific energy up. Here's I'm showing, this is sort of single crystals between 1 and 2 micron. You get about 640, and we're now approaching actually in other work about 700 watt hours per kilogram in this DRX. Again, these materials cycle extremely stable. This is the energy density. This is the capacity. Sits roughly at 190 to 200 milliamp hours per gram. And energy density and voltage are very stable. So where do these materials sit, sort of in contrast to the larger cathode landscape? So I've plotted here the specific energy at the cathode level and the energy density, and try to compare it to other materials. Like these are the NMCs here, and these are the LFP. And LMFP is still kind of a bit of a research product. We don't totally know where it's going to end up, but probably somewhere in this green circle. And what you see is that the micron size DRX, which is this one, and this is the nanometer size DRX, sits in specific energy, kind of at the low level of the early NMCs. Partially the short spinel, which is the material I showed you earlier, which is a heavily milled material, sits way up here. But to go back to the lessons sort of we've learned at the beginning with LFP, because delta DRX only uses manganese as the redox couple, and the top of charge only uses manganese 4. There's no oxygen redox. You would expect excellent thermal stability from these materials. And so what you really expect that at the pack level, we know that if you get thermal stability at the pack level, you get major benefits. These materials would actually even be in specific energy and energy density quite competitive with NMC materials, though they are potentially a much cheaper version and a much more earth-abundant version. So with that, I think I'll summary so we can have some discussion if you want to. Again, one takeaway is that in nano DRX, first of all, DRX is a whole family, so don't get confused. There have been nickel-based DRXs, there have been vanadium-based, chromium-based DRXs. In the heavily milled powders, we've certainly seen capacities well over 800 watt hours per kilogram, even up to 1,000. In the sort of more practical materials, the larger single crystal materials, I think we're best number now we've seen is 675 to 700. And of course, the crystal density being 4 grams per cc, you're better than LFP on crystal density, right? We see no observable capacity fade, and fairness, these are still half cells. We are about to start in the consortium a full cell program ahead of schedule. Our consortium was not supposed to do full cells, but because we feel we're ready, we will do that. And there will, of course, inevitably come up the question of whether there is manganese dissolution or not. But the promising aspect says that these materials use only lithium, manganese, and titanium, and lithium is going to be by far the most expensive element, and that so they are an option for inexpensive, high energy density, and maybe most importantly, thermally stable cathode materials. So with that, I thank you for your attention, for sticking with me. So I see there's some questions in Q&A. Maybe, Corsin, I'll let you handle that.